Hello, everybody. Let's do a quick lesson recap of today's discussion about infinite series. So informally, we could say that an infinite series converges if it approaches a single finite value as you add more terms. Otherwise, we say it diverges. And we're going to refine this idea in just a second. But an easy example would be the infinite series where you add 1/2 to itself an infinite number of times. So pretty clearly, this series diverges because as you add more terms, it just keeps getting bigger and bigger towards infinity. So that's one way that a series can diverge, one way that it can fail to approach a single finite value. And it might be useful now to introduce a little graph. So you can imagine here are some term numbers. Here's 1, 2, 3, and so on. So after the first term, the sum is 1/2. After the first and second terms, the sum is 1. First, second, and third terms, and we've got 1.5, and so on. So what I'm graphing here aren't the actual values of the individual terms, because if we were going to graph the values of the individual terms, those are always at 1/2. Here's 1, here's 1/2. So like term 1 is 1/2, and term 2 is 1/2, and term 3 is 1/2, and term 4 is 1/2. So we could say that this was a graph of the value of each term. This is a graph of what we call the partial sums. And partial sums just mean the sum of the first some number of terms. So the third partial sum is the sum of the first 3 terms. The fourth partial sum is the sum of the first 4 terms, and so on. So you can see that as you add more and more terms, the graph of what the partial sums are doing is going to show you what's happening with the entire series as you add more terms. And here it's pretty clear that the series is going towards infinity. Okay, so let's think about this one. Excuse me. So here, if we were going to graph the partial sums, you see alternation. So the first partial sum, which is just the first term, is 1. And then the partial sum of the first 2 is back down to 0, and then a 1, and then a 0, and a 1, and a 0, and so on. So it just alternates forever. And so this series also diverges because we're alternating forever. We're not actually getting closer and closer to a single finite value, which is what you'd need to converge. So this is a different way that something can diverge. It's not going towards infinity, but it's continuing to oscillate forever. Somebody also pointed out in the discussion that you can make this sum seem to equal different things depending on how you group the parentheses. So if we group this as 1 minus 1 plus another 1 minus 1 plus another 1 minus 1 and so on, it appears to be just a bunch of zeros that are added up. So that way of adding up makes it seem like it should equal 0. However, if we group it this way, have the leading one, and then group together grouping of 2 after that, this is 0 and this is 0. So this way of grouping the addition makes it seem like the entire series just equals 1. And indeed, you could make this series equal anything that you wanted to by controlling how you're grouping. So the moral of this story is that things that you can do, such as choosing the order in which the addition happens, that are okay when you have finite sums might not be applicable to infinite sums. And indeed, that's the case here. You're not allowed to change how the ordering of the grouping for an infinite sum, because that can actually change the value of the entire infinite sum. All right, so far we've got an example that diverges, another example that diverges. This was the first one where we had a couple of arguments that it should converge. And we saw 2 different arguments. The first argument was, imagine each of these as a jump. So if we're sitting here at 0 and we jump a distance of 1/2 for the first term, we end up at 1/2. And then for the second distance, a fourth is half of the remaining distance. So if I'm going to add a quarter, now I'm here at 3/4. An eighth is half of the remaining distance. A 16th is half of the remaining distance, and so on. So it seems like this infinite series, I'm continually jumping half of the remaining distance, and it seems sort of intuitively clear that this should be approaching the value 1, because if you add this sequence of jumps, I should be approaching the value 1 here. So That's a good intuition. It's not a proof, but that seems pretty compelling. A different example that we saw was, what if we imagine a 1 by 1 box? So this area is a half, like the first term. The remaining area is a half, and so half of that would be an area of a quarter. So now I have shaded a half plus a quarter. The remaining area is a quarter, so half of that would be an eighth. Half of the remaining area would be a 16th, and so on. So just like the last example, instead of jumping towards your end goal, here each term is adding half of the remaining area. And you can see that if I were going to continue this process infinitely, the sum of all of these halves of the remaining area approaches the area of the entire box, which is just 1 times 1. So that's a second demonstration that maybe the series converges to 1. Another way we could do this is, let's actually look at the sequence of the partial sums. So 4 terms should be enough probably. So the first partial sum is just the sum of the first term. This is the sum of the first 2 terms. This is the sum of the first 3 terms. And the sum of the first 4 terms. 1/8, 1/16. Okay, so what do each of these equal? So this is 1/2. If I take 1/2 and add a fourth, let's put it all over a denominator of 4. So 4 divided by 2 divided by 4 is the same as 1/2. So 2/4 plus 1/4 gives me 3/4, which you can see in this jumping diagram. 3/4, if I multiply it by 2 over 2, is going to give me 6/8, plus 1 more eighth gives me 7/8. If I multiply it by 2 over 2, that gives me 14/16, plus 1 more 16th is 15/16. So it seems like I can guess a general rule here. The rule appears to be, in the denominator, I've got 2 to the n, and in the numerator, I have 2 to the n minus 1. That seems to be the pattern here. So if we were going to do this more rigorously, you would actually need to prove that this is the equation for the nth term. But let's just assume that it is. If we go back up to our informal definition, we say a series converges if it approaches a single finite value as you add more terms. Well, this sequence of finite sums shows me what the entire series sums to as I add term after term after term. So it's like, this is what it is after 1 term, after 2 terms, after 3 terms, after 4 terms, after n terms. So what we want to know is, what's the limit of those partial sums as the number of terms approaches infinity? In other words, if I was going to graph these, are they approaching a single number? So let's look at that. Let's look at limit n approaches infinity for 2 to the n minus 1 over 2 to the n. Let's break this into 2 pieces. We'll have 2 to the n over 2 to the n, and then n approaches infinity for 1 over 2 to the n. Okay, so I've actually used a theorem here that I didn't prove to you. When I split this into 2 parts, we have that the limit as n approaches infinity of this minus this. And what I've done is I've said that limit of one thing minus another thing is the same as if I take the limit of the first thing and then separately I subtract the limit of the second thing. That happens to be true, but it's a theorem that you're going to prove probably in the first couple of weeks of calculus. For the moment, let's press on. So 2 to the n over 2 to the n is 1. So this is just equal to 1. And then what's this? So here we've got 1 divided by a number that's getting larger and larger and larger as n approaches infinity. So that approaches 0. So here we have confirmed our intuition that this infinite series should be approaching 1, but we've done it using the definition, which is that the sequence of partial sums should equal 1. Sorry, I don't know if I just said the right thing. The limit of the sequence of partial sums is approaching 1. All right, you can come back in another video and we'll do this the same way, but thinking about this as a geometric series. Because remember, we've already shown a way of deriving what is the nth term for a geometric series. It's not this. Remember, it was the first term minus 1 more than the last term divided by 1 minus the growth factor. So we can do this same derivation all over again, but using the equation that we got from our earlier derivation for geometric series. And actually, you can do that the same way for any geometric series. And so we can see which geometric series are actually going to converge and which are going to diverge. So the next one that we discussed was this series. This is actually a famous series called the Harmonic series. And here we disagreed. Some people thought that this infinite series was going to converge. And their argument was something like this. Like, imagine this as a sort of a jumping scenario. Here, you're going to jump by 1/2. And then you're going to jump by 1/3. And then 1/4 and 1/5 and 1/6. So the argument is, even though you're adding an infinite number of things, the things that you're adding are getting smaller and smaller, approaching 0. And eventually you're going to be adding things that are so close to 0, it's like you're hardly jumping at all. So maybe that condition is sufficient for the infinite sum to converge. And I'm not affirming or denying that, but I think that's an interesting kind of an argument. Someone observed that actually, as soon as you add these three are already larger than 1. So if we add 1/2 plus 1/3 plus 1/4, we've crossed 1. But there's nothing saying that the original argument isn't right, and like maybe there's some other number like 19, and you're adding smaller and smaller hops, but you're never going to cross 19, for example. And it's probably not 19, but you see what I'm saying. Like, just because we cross 1 doesn't mean that it might not converge to some other value over here. So that's the argument on the one side. Adding terms that approach 0, maybe that means your infinite sum converges. Somebody else said, look, there's an important difference between this series and this series, and it has to do with the function on the bottom here. Here, each term is given as 1/2 to the n. So the denominators here are growing exponentially. Here, this is like each term is 1/n. So the denominators are growing linearly. In other words, here the denominators are getting larger and larger very, very quickly, and here they're getting larger and larger somewhat more slowly. So maybe the speed at which these terms are approaching 0 matters for whether it converges or not. And I think that's also a very interesting argument. The last one we looked at was this, which is just the harmonic series, only now we're alternately subtracting and adding alternate terms. And so somebody made a very nice argument here about, let's imagine each of these as being a jump and see what happens. So if we start at 1/2 and then we subtract 1/3, a third isn't going to take us all the way past 0 because a third is smaller than 1/2. So it's going to take us somewhere that's not close to 0. Okay, so then when we add a fourth is not going to take us past our original half because a fourth is less than a third. And similarly, when I subtract a fifth, that's not going to take me as far as my fourth. And then when I when I add a sixth, same story. So it's sort of like, it seems like I'm going to be cycling closer and closer to some mystery value that I'm actually converging towards. So again, I think that that's a really cool and interesting argument. We had a couple of possible counterexamples to that. We seem to be cycling in. I would say, like, how do you know that it's actually converging to a number instead of oscillating forever in a very small way, the same way that our example number 2 did, where we were adding and subtracting ones. So that's a thing you could think about. But this is a very sort of interesting, telling argument. The result, you're going to learn a lot more about series in calculus, and I don't want to steal all the thunder from calculus. But there's one result that you're going to use a lot in this class, and it's the sum of an infinite geometric series. So we already saw the example of the geometric series that looked like this, 1/8, 1/16. There's other geometric series like 2 plus 4 plus 8 plus 16. Like, very obviously, this is diverging. This one's converging, we thought. Oh, and we proved, indeed. What about other geometric series? Like, how do you know when they're converging and when they're diverging? So come back in the next video and we'll prove the following result. The result is if you have any infinite geometric series, so for example, a1 plus a1 times r plus a1 times r squared and so on to infinity, you can notate it using sigma notation this way. And if you add up all those terms, they're going to converge to the first term divided by 1 minus that multiplying growth factor. Because remember, the way we get from each term to the next term is by multiplying by r. But that's only true when the magnitude of r is less than 1. So in our example where it was 2 plus 4 plus 8 plus 16, here the r value is 2, because I'm multiplying by 2 to get from each term to the next. So clearly that's diverging, and because the magnitude of r is not smaller than 1, this result doesn't hold. But for the example from earlier in the video, when I've got 1/2, 1/4, 1/8, 1/16, here the r value is 1/2, and the first term is 1/2. So this result predicts that we should have 1/2 divided by 1 minus 1/2. 1 minus 1/2 is just a half, so half divided by a half is 1. And that was the result that we proved earlier. So this is a useful general formula to know, but like I said, come back in the next video to see how it's derived and to understand why is this condition true.